Hey guys, how's it going? Welcome to another episode of Ferris Makes Hardware. This is episode 26, and we're continuing on rebuilding the system bus after moving everything to Kaze, the Rust HDL that I'm working on. Not much has changed in that, which is nice, as we've implemented more of this in the last week. I think I might start having to look at the synchronous memory API a bit more because I might want to add byte enables for writing. But I'm not 100% sure about that yet, so we'll see how that goes. One thing that I did discover within the last few days, actually, is this draw.io tool. And I feel like I had looked at this before when looking at like ways to document the system. And I think I remember rejecting it because I wanted to have a textual representation of these diagrams. And so I ended up going with dot and graphviz. But what I found is that it wasn't very easy to modify or very enjoyable to modify, and it was kind of hard to just throw things down. And really, all I want for a lot of diagramming that I do is just squares that have text in them, and then you can connect arrows, and the arrows stay connected, right? Like it doesn't feel like a big ask, but a lot of tools are surprisingly hard for that. Either that, or at least they're unintuitive to me, and I had a hard time just doing that. So I think I tried Inkscape. I tried more that I don't remember right now. But anyway, I've landed on this, and so I've actually gone and changed all the documentation. So I deleted all the dot stuff in the Xenoing repo, and I just replaced it with this draw.io file and then it exported SVG. So I think I'm gonna use this tool to continue this diagramming stuff. But what I wanted to show here is I actually did a better diagram of the Xenoing bus architecture. Can I turn off these guides actually? Grid Control-Shift-G, it says. Indeed, there we go. Nice. Oh. Okay, fine. So most of you guys have seen this diagram because I keep drawing it in Paint. But this is more or less what it's going to be. And I also did something cool. I drew out kind of what I want eventually. And then I modified it a bit, and so I grayed out a bunch of the stuff for things that are sort of coming later. So this stuff that is not grayed out is kind of the intermediate goal. So I'm designing a bus architecture that can handle multi-master, multi-slave, all this other stuff. But for the time being, I think multi-master isn't actually going to be necessary with this architecture here. And I'm putting off like the DMA and then the arbiter that arbitrates access to like display DMA. I'm also putting off the display and the display DMA because I think the most useful thing right now is to get the CPU up and running again and be able to talk to the CPU over the UART. And I want to actually implement interrupts this time for the CPU and then have a UART receive interrupt. And via that, I want to be able to send messages to the Xenowing. So I'm thinking that this next little implementation is going to be sort of tethered to my machine, to my PC. And I want to change the boot ROM such that when it boots up, it's going to actually request the program from the PC over UART. So it's going to send like a file open, file read, whatever messages, and then the PC is going to respond. And I think that's going to be a good way to do that. I think because the only receive that I had done before is I had hard-coded, like essentially hardwired, a unit that whenever it received any data, it would assume that the PC was trying to reload the ROM, and it would hold the system and reset and then load that and then start up again. And I think that's not what I want to do this time. I think what I want to do is not reset the whole system, and then whenever that happens, I just want it to load a new program ROM, which the CPU will actually do explicitly, I think, and then reboot itself, which I don't think it'll actually reboot. I think it'll just jump to the beginning of that program again, which will do a bunch of init stuff because that's what that's normally meant to be doing. And then later I can use that same code, but I can make it like read from, for example, the SD card that's on the board. And we can, similar to how I implemented the I2C for the other board, where I just kind of bit banged it. I'm thinking I could also do the same for the SD card, at least for initial implementation. And I can do that sort of with this program reload feature, and then when I get it working, then I can move whatever of that into the boot ROM. So I think we're kind of going to approach something that's a little more traditional in that sense, but I think it's going to be easier to debug because I think the most important thing is to get this running and then be able to talk over UART such that I can implement like a command processor as part of the main ROM. And then at any given moment, I can, for example, go into a debug mode by controlling it from the PC, for example, and then have it just respond to whatever messages I send. And then if I can implement like memory read and memory write, I can use that to transfer data into any of these other devices under test. In particular, the GPU, I want to just start developing like that, where I just talk to it from the PC via all this other machinery, and then actually have it render stuff that I can pull back through the UART before I even get everything displaying from memory again with this DMA. And I think that'll be kind of the most sane way forward. And in the meantime, a lot of this stuff, like this UART receive code, is going to get a lot of testing throughout the development of the project. And I think all that's going to be basically necessary. So that's what I'm thinking, and that's what I'm working towards. And now that I have this little diagramming tool, this is a lot easier to communicate, which I think is going to be really important. But yeah, eventually I want to have a DMA, which means this is actually kind of important. I want to have the DMA be able to read from this memory bus and write to the system bus at the same time, and that way it'll be able to achieve maximum bandwidth here. So you kind of need these two channels, and you end up with this little crossbar here. And again, making sure that works as expected is going to be a bit of a challenge. But again, I think the approach that I'm going for now is that these boxes down here are essentially going to be instantiations of what I'm currently calling Buster. That's what we worked on last week as well. And that's just a composable bus unit is the point. So all these buses are going to be 128 bits wide. And I think I'm going to actually change the memory map as well, such that all of these have registers that start on 16-byte addresses. And so then when the CPU accesses them, it's just going to access like individual 32-bit words, because the CPU only has a 32-bit bus, and there's going to be this 32-bit to 128-bit bridge here. But there's actually another advantage to that, which is that all of the addresses for MMIO registers are going to have nice looking values in hex. So I think that'll be kind of cool. Rather than like incrementing by 4 bytes every time, they're going to increment by 16. So it's going to be the next digit over, and they're just going to increment by 1. I also considered actually having the system bus kind of up here and then being driven after this bridge. Like this would fan out or something like that. I don't remember. But what that would mean is that I would have to, what was I going to say? Just lost my train of thought mid-sentence. Maybe I'll just get back to that later. Oh yeah, I remember. It would mean that, so the reason I have this down here is so that the DMA can read and write to DDR memory at full 128 bits, 8-bit, or have a whole 128-bit data path, to maximize the bandwidth that we can get from the memory controller. That's all. That's kind of what all of these bus widths are built around, is maximizing the bandwidth here. In particular, this arrow here, making sure we get max bandwidth through there it means we have a lot of complexity elsewhere, but I think that's natural. Anyway, because this has a 128-bit wide bus, I also want to have a 128-bit wide bus to the internal memory of the GPU, for example, and also the internal memory of the vector unit when we get to that, and maybe an audio unit as well. So in order to do that, at least those need a 128-bit bus that's connected, that the DMA can drive. So if I wanted to move these up here and make them only accessible via this 32-bit CPU bus, I would have to have an additional bus for all these units that the DMA could read. And I thought it would overall be simpler if everything was just connected to a 128-bit bus, except the CPU, of course, which only has a 32-bit bus. I think that's fine. Yeah, I'll probably still make some shitty paint drawings. I mean, I think they're fun because you don't have to take them too seriously, and they're easy to do. But I do like the clarity of a proper diagram. By the way, hi to guys in the chat. Daniel Collum, or did I say Collum? And his brother Daniel Rowe. Daniel Collin, the Geek Pirate, Dark Second, DDR Boxman, Chief Detector. Good to see you guys. Or good to see your names in the chat, I guess. Whoops. That's funny. But yeah, I think I got to a point where I had basically implemented what I was thinking for the Buster. And at least the current generation. And I started writing tests after that. And I actually GitHub had an outage that ended up causing a crates.io issue. So I found a problem with the CodeGen in Kaze that internal memories that had a Boolean data type, element type, actually generated bad code because I think I just output a zero literal, which doesn't work for bools. So I had to fix that, and then I published it, and then the crate publish failed. So it took me like another day or two to actually get that sorted. But the DMA engine is not going to be called Booster, but that would be funny, especially if I pronounce it like Boosta, like they do at Tursock. But no, I'm gonna. I think it was going to be called Bit Thruster, I think is what I wanted. No, I actually don't know. Oh, did they do a report on Reddit? I didn't know that actually. I sent an email the day after and didn't check Reddit, so that's kind of funny. But they were extremely quick to respond. Like they were really good about it, so that was pretty cool. Wanted to point that out. But I kind of want to see that update actually. If you have a link, that'd be great. It's old news at this point, but I still want to see what it looks like. Yeah, it's fixed really fast. They had to do some manual stuff. Like I think they removed the version of Kaze from the database at least, and then I just republished and it was fine. It's really easy. Yeah, the Rust community is awesome. Huge selling point. Yeah, I think if I go into Sim Buster, I can do cargo test here. Should test stuff, yeah. Daniel Cullen, when it was after the stream last week, I went to publish a fix in Kaze, and then that publish actually broke, and it was due to an outage that GitHub had, and I guess it affected crates.io. So it looked like the crate was published, but then docs.rs didn't get updated, and I couldn't actually use the new crate version. That was the symptom. I don't really understand what happened, but then I emailed them and they handled it really quickly, like the following day. So it was really good. So I had the proper version published and fixed by Saturday, which would have been sooner if I had responded sooner, but I was busy on Friday. But yeah, so the Buster so far, the implementation that we have here. Again, I want it to be like sort of this reusable unit. I'm going to start making a new drawing on the fly here. Make a new one. Blank diagram. Yeah, self-hosting would have solved that for sure. I'm also just learning this software, but I want to get better at drawing proper diagrams, so we're just gonna live with this. Anyway, this is a diagram of kind of what I want Buster to be. I can do a heading here. I haven't drawn the idea for this, so I think it's a good opportunity to do that. So the idea behind Buster is that you want to have something that can sort of build like composable bus units, and it needs to handle, for example, unpredictable slave latency, for example. And by the way, I was talking to one of my colleagues at work, and I was talking about masters and slaves, and they said that terminology is kind of going out the window. And I thought about that, and I thought it's a bit frustrating because that describes a particular relationship. Like I guess people did I talk about this last week? I must have. But you have like the master and slave explicitly says that one of them is in charge and the other one does whatever the master says. And some people were proposing like using master and secondary, which I didn't quite like because it feels like it doesn't describe the same relationship. I thought about using dom and sub. I guess leader follower could work. Maybe I'll adopt that actually, because it doesn't really matter that much for doing this. But I thought that was funny. But the point is, you create a buster, and then you add as many. I'm gonna continue using master because that's the terminology I've chosen up until now. So you want to add essentially multiple masters, as many as you want, basically. And then these are read ports, or actually they're read or write, but they're explicitly mastered. And then you can also create one or more slave ports. And the idea is that these wouldn't be named; they would just be added in order. And I've also been thinking about like priority, and I think I'm just gonna, for simplicity's sake, have all these have the same, or have like fixed priority, or fixed. Man, I feel like I'm slow at talking today. But fixed, is that the word? I think that's priority is the word, but I also think it's not the word. I do not know why that word's escaping me. I think it's priority. Anyway, so if this one is asserting a read and this one's also asserting a read, then this is the one that's going to go through. That's kind of the point. But again, any one of these can have like variable latency. So if one of the masters issues a read, you need to make sure that you can handle that read can come back at any time. And also these different masters could be issuing reads. So it's really reads that are the problems. Like writes are pretty easy because you just kind of do arbitration and then the read kind of goes through and it's fire and forget, but reads coming back are more difficult. So the main thing here is that we have a FIFO here, which I think, what did I call this? I called it there's a master FIFO and a data FIFO currently, and this is going to need to be split up because currently I'm just kind of implementing like one version of this, and then I'm going to generalize after it works. So I guess I can draw what I have. Maybe that's useful because I think I only have one slave and then two masters that are hard-coded right now. Let's start with that. But eventually this is all going to be really? Oh, it's because it's connected here probably. Eventually this is all going to be created programmatically and on a case-by-case basis, because if we go back to this this other diagram, you can see that several of these have, for example, this has 3 masters, and this one is only going to have a read port, but I'll probably just instantiate the entire like read-write for that to make it easy. But this one only has 2 masters, this one only has 1, this one has 2, and then this one fans out a lot for a lot of different slaves. This one has 3 slaves, or I think it will have 2 eventually, but right now it's going to have these 2. So I want to be able to make one unit that can kind of handle all those different cases. And I think that's kind of a good idea to do also, because I don't think it's terribly complicated, and it's kind of nice to do all of that at once and then just have this composable unit. Because one of the things that I think a lot about when I'm working on this project is that this is like, I think of the Xenowing as like kind of my big hardware project that I'm going to have for a long time, because if I do this reusable bus unit and I have this reusable CPU, then I can kind of hook whatever to it, and I can make different bus architectures and sort of play with these ideas. If I wanted to make a sound chip in a weekend, I kind of have the framework to be able to do that. So up front, sort of solving these problems and making sure these things are robust, I think is a good idea. But yeah, this is called, there's one, this is the master FIFO. And then there's another one, which is the data FIFO. And I think make these skinnier. Something that's going to be important is that I think each slave is actually going to need its own data FIFO eventually. Make these a little wider to make sure we fit the names. This is the problem with a lot of these proper tools, that I end up tweaking alignment a lot, but I think it's going to be fine. So the issue here, actually I'll draw some more boxes first, and then I'll talk about these. I want these to be skinnier because they're FIFOs, but there's some of these that are going to be simpler. So I had the issue arbiter, and issue arbiter, and then the issue unit, and then the return arbiter. These were all different. So the idea here is that there's, let's say if each of these were to issue a read, for example, these are going to go here. So the first thing is that there's this arbiter. And that's going to essentially decide which one of these two masters gets the bus on any given cycle. And again, there's fixed priority. The ones on the left have higher priority always. That just makes it easy. And I might actually try to support cases where these can like read and write past each other at some point, but not in this generation. So we're going to do that. So the issue arbiter essentially just muxes these signals and performs some arbitration, and then this goes to the issue unit. And then the issue, I think I've only handled reads so far, and that's because that's more complicated. I think writes are going to be easy, so I think I've only implemented... Oh, no, I did do writes as well. I wonder if that's tested yet. No, wait. No, I've only done reads. Forget I said that. And then this actually has to do some kind of special stuff, because this issue logic, we actually need... I'm going to do a dashed arrow, I think, for this valid signal that's going to be here. And the point of this is that this is going to tell the issue whether or not this slave is actually ready to receive. And so when we're able to like issue a... Actually, let's just make this solid again. And then we'll just add arrows in the ends. So the idea is that if one of these masters is trying to issue a read, it's going to only do that when the slave is actually ready, and that's why this is a bidirectional arrow here. And so when it's ready, it will issue the read to the slave, and it will also issue a bit that determines which master issued that read. And the reason why we do that is because eventually that data is going to come back, and then we need to decide which master to give that data back to. So that's why we have this master FIFO is for that. I think I'm actually going to separate these, by the way, into a couple things. Oops. Because I think it might be clearer if we actually separate some of the ports here. So I think I called this... I'll add some text. Oops. What did I call these? I called these... We can just call these master 0 issue and master 1 issue. And then it makes it a little more clear kind of what's happening here. Clarity is paramount. So yes, this guy will hook up to there. This guy will hook up here. And that connects to this issue logic. And then we have the slave issue, which is here. And so we'll call that SI for now. And SI has a couple important things. In fact, I think I can just make all this tighter. I'm going to put this kind of documentation into the repo, I think so. I think it's worth spending some time on this. So this has... Oops. I'd like this to snap. Can I snap? Whatever, not terribly important. Yeah, so this issue here, yeah, I think I actually want to draw a second arrow for ready. So it's a bit convoluted here because these issue buses actually have address and data. So I might want to make those thicker, but we can worry about that later. And then we have slave 0 ready, which is important to distinguish. Or slave ready, so I'll call SR for now. Just gonna clean all this up because I can. Yeah. So yeah, so this slave ready gets routed to this issue unit here as an input. And then this will issue data if the slave is ready to receive. And I should have, I'm just going to swap these this way so I don't have to move the arrows around so much. Oops. Appreciate you guys' patience here. Again, I think it's worthwhile spending time on this. Right. So if the slave's ready, then it will actually be able to be issued. And it's going to issue this, and then it's also going to issue data into this master FIFO, which I might make sideways, actually. No worries, Chief Detector. No worries. Hey, Alkama. So yeah, so when one of these masters is trying to issue stuff and stuff is ready, then it will issue, and then it will also dump whichever master was able to successfully issue into this FIFO. And this only happens on, I miss you too, Alkama. This only happens on reads, because on writes, again, they're like fire and forget, so you don't need to do any of this stuff. This is looking nice, you guys. That makes me happy. Oh no! I did not expect that. I'll just fix it. Deal with it later. That was kind of funny. Yeah, something like this. And then eventually data is going to come back. That's the sort of other important thing that happens here. And let's actually write these out. Master 0 maybe. And then eventually this data is going to come back. And so we can copy this perhaps. Just got the arrow, that's fine. Fine enough. The reason why I wrote this out is because now this is going to be called slave return. Right, because this represents the data that's going to be coming back. And here, I think I'm going to feed that straight into this FIFO. FIFO, FIFO. Doesn't really matter what you want to call it. Like this. And I think this return arbiter, I think that just handles the rest of it. Yeah, I think it just waits for data to be ready, and then it issues reads, and on the following cycle, the correct data gets routed to the correct master, depending on the data that was read from both of these. That's how this works. This goes into this return arbiter, and then so does this data FIFO. And then this fans out again. Articanus? I'm not sure how to say that, but thanks for the follow. Appreciate it. Yeah, like this. Probably gonna have to adjust all these arrows again after I'm done drawing all these diagrams, but that's okay. Don't really care. Basically this. We can just make this stuff more compact. Why don't we? And I do actually want to do this. This is about what we want. I think it's that one we want to get. Yes, perfect. Perfect. That's what we want. Beauty. All right, but I think this makes it fairly clear, right? We have maybe I can make this even clearer by moving this. Yeah, I like that. I like this. So at any given cycle, we let one of these issue a read. One of them is allowed to. And again, 0 has priority over 1. And once that's able to be issued, as long as this one's trying and the slave is actually ready, and there's no buffering in that part of the pipeline. And as soon as that's issued, we issued which master into this FIFO. This FIFO also has to have room in it for us to be able to issue a read. Writes won't actually have to do that, which will be nice. And then eventually data is going to come back from the slave, and what we do is that gets into a FIFO, and then as soon as the data FIFO and the master FIFO both have data in them, then this arbiter can issue a read to both. And then on the following cycle, it's going to get data from both, which is kind of guaranteed by the interfaces here. And then it's going to drive a mux here. Or actually, it sends the data both, but it tells which one of these is valid depending on the data that came from the master FIFO and the data just passed through. So this is the buster. This is sort of the idea. But this is like a version, I don't know, 1, I guess, or 0.1 or something, because this is what I have implemented now, but eventually I want to be able to add multiple masters and multiple slaves. And maybe I'll change the name. Leader follower kind of makes sense, I think. In fact, why don't we adopt that now? Leader 0 issue. I actually don't like how long the word follower is. Primary and replica kind of sounds cool. I'm literally looking at alternatives for for these units. Yeah, I mean, this is draw.io, which I'm really happy with. It seems primary and secondary have been used, or primary and replica have been used in a lot of places. I'm gonna do that, primary and replica. I think we can live with that. And then we can go in here and change all of that. So master everywhere becomes primary, and then here we want to use a different convention, and then slave everywhere is going to become replica. And now all the tests are broken too, so that needs to be fixed here, which is easy. We should just be able to do primary and replica. Easy. Okay, so I'm just going to save what I have drawn here into the repo right now and export to SVG. I think I exported the other one with 0 for border width. Maybe I did 10. I don't remember. I can actually just look. Yeah, that one has no border. Let's follow that. Makes it easy anyway. We can call that, yeah, buster.svg in the repo. Nice. And again, this is like a preliminary design because eventually we want to be able to add multiple primary ports and multiple replicas. But I'm going to commit what I have just to commit to this name change. I think the bus topology we don't want to change, actually, because I don't think we did anything meaningful in there. Did I not save this with the right extension? I think I did not. Yeah, there we go. Explains that. Yeah, I think that's nice. And we can just ignore that. Great. So yeah, so in testing this, I wrote some basic tests. So I have a test that will just do a single read for primary 0 and make sure we get the right data and that primary 1 wasn't acknowledged or it didn't return data to the other primary. I did the same thing for primary 1. I did another version where I read like a bunch of data. So here I made some data of whatever size and I had it read all of that data until it was done. And then I think I did exactly the same thing for primary 1. And then I think that's as far as I got. So I think I was going to implement writes next, again with this single replica kind of thing. But I'm wondering actually. So the irony here is I started with reads because I knew they'd be more complicated, and especially with multiple primaries. But I think actually in this initial design there aren't any cases where we have multiple primaries. So it might be that I want to start instead of starting on writes, I might prioritize multiple replicas and getting that to work nicely. So I think I might just take this design and yeah, go for that first. Now that will become a bit more complicated because each replica needs its own FIFO, which that's not that bad. But right now it's convenient that we can issue reads to this and to this, and we know that the data will be in alignment. But is that what I wanted to say, or is that not what I wanted to say? Actually, yeah, we have to kind of redesign this. Let's actually just add another replica and think about it, and we'll work out everything that way. Articanes, I really don't know how to say that. I apologize. This project is called Xenowing, and it's an FPGA implementation of like a late 90s fantasy console that I'm inventing. That's what this project is. I think that's the shortest description I can give. Like a late 90s fantasy game console with a rasterizer and some fun stuff. Although it doesn't really have that yet, just has prototypes. It does have a working CPU and a bunch of half-finished other stuff. So yeah, this is going to be called replica 0 return now. And we also need to have return or issue and ready for all the different replicas. So this is going to need to fan out more, but I'll worry about that later. This is the more important part now. I think this whole thing here gets duplicated. And now herein lies the problem, because these FIFOs always have 1 cycle latency through them. And that's going to be problematic for this FIFO, because we need to, in order to know which one of these to read from, it's actually not this one. I think we need another one. Another FIFO here, because we have the primary FIFO and then we also have the replica FIFO. Because we need to know if we issue to read, now we actually need to keep track of which replica that read goes to. So yeah. So if we issue a read, we need to say which primary it came from, which replica is going to return that read. And this is actually critical, because this FIFO here, like the data is going to come back into these FIFOs basically any time. So the case that we need to worry about is if even if you just consider a single primary, if a primary issues a read to replica 0 and then to replica 1, and then replica 1's data comes back first, which it can, that might come back on the following cycle, whereas replica 0 might come back 20 cycles later or something. We need to store the return data in these FIFOs such that we can pull the data out whenever we get data that is returned from the replica that we expect. That's a good way to sum it up, I guess. So essentially we need to serialize all of the issues, and then we're also going to serialize all of the reads coming back. That's kind of our goal here. So what we need to do is this again needs to go into this arbiter, this primary one. That one's still easy. Whenever we issue a read from either of these FIFOs, we're also going to issue a read to this primary one, and then data goes back to whichever of the primaries that issued the read originally. That one's fine, but I think we also need to make this even bigger. Adjust the arrows again. I don't know how to make this not snap to this box, these arrows here, so we're just going to live with a little bit of misalignment. Hey, 286 Tech. Yeah. Something like that. Might even want to make this taller, actually. We'll see. Because I think we actually need this. We need a buffer, because these FIFOs always have 1 cycle latency through them. So I think what we need to do is we need to read data out of this FIFO and into this buffer. And then we actually know what it is. And we need to know what it is in order to issue reads out of the correct FIFOs here. Let's actually do that here. And then this one can issue back to this arbiter. So this arbiter has a somewhat complex job. And then we also need to do this buffering correctly. I think I'm also going to fix up some of this stuff to make it look a little nicer. Yeah, so it's gonna look more like this. I actually want this aligned here. Yeah, I think this is ultimately the design that we need. And then whenever we add replicas, we basically add bit widths here and additional of these paths and also additional of these paths, which I still need to replicate in this diagram. And then as we add additional primaries, we add additional bits here. And then this fans out more, this fans out more. But everything else kind of stays the same. So there's sort of this divide here. Where this stuff gets more complicated as we add replicas, and this stuff gets more complicated as we add primaries. But I think it should be fairly clear to see that this is general enough. At least I think it is. I think I'm just going to add some margins and stuff here to make this look a bit nicer. What happened with this arrow? Oh, that's what happened. I see. I see what I did. Something got messed up here. That's fine. Something like that. I think I'm just going to rename these N to kind of show that they're going to be sort of replicated. I think this is more or less the design we're going to end up with. And this part's really the only part that gets a little more complicated, is that this replica buffer, or there is a replica FIFO at all, and that it needs to pull data out into this buffer so it can see it, so that the arbiter can then issue to the appropriate FIFOs here. But again, I think this captures basically the entire behavior. It's not, I don't love having all of this, having all these FIFOs in here, because these will get really wide. So it'll be a fair amount of memory in a lot of these FIFOs, but timing wise, I think that'll be okay, because these FIFOs are essentially going to act like registers. So you kind of decouple a lot of the timing in these paths. Not this path, actually. So as we stack multiple ones of these on top of each other, I think this path might get critical, in which case we might have to insert registers and stuff here. But yeah. Now the hard part is it can be difficult to at least for me, to like envision the behavior of this, because like one of the things that can happen is, let's say we issue one read, and it goes to replica N from primary N. It doesn't really matter. 0 and 0, we could say. Then we get 0 pushed on here and 0 pushed into here. And then that 0 down here is going to be read out pretty much on the next cycle. And if the data comes back then on the following cycle, everything should be ready to... I think it adds one cycle of latency where you might not otherwise need it in that case. So on cycle 0, let's say we get the issue through and we write to these FIFOs. On cycle 1, let's say the data comes back and then this is read into here. And on cycle 2, you'd be ready to issue this and this. And then on cycle 3, the data would go back. And I think that all works out. And you can only issue into these FIFOs when both of these are available. Yeah. Yeah, there's a lot of this bus arbitration stuff that gets complicated. But I think that works. And then so these FIFOs are going to often be like one off, but I think they need to be, and I think it'll still be okay. I don't think we'll ever overrun these, because you'll never write into here unless this one's free as well, which this one only drains when we actually have data coming back. So yeah, skid buffers, because those are used if you like to have, I mean, I guess this wouldn't be a skid buffer. Maybe I just need to look more into those. Oh yeah, pipelines are ready and valid. Right. But I guess the point of that is it allows you to like return one word of data before you tell the thing that it's actually busy, for example, or that it's full. I guess is kind of the point. But I guess these FIFOs kind of act like that in this case. I'm not entirely sure. I'm not an expert here, so I don't really know. Gotcha. That seems like a good pattern, but I think we actually need, I guess this one here could be a skid buffer, this replica buffer. Because I think we need FIFOs here in order to hide latency for these, because this could take like 20 cycles to come back, so we'd want like a 20 deep FIFO. But in order for this one to not always have that 1 cycle latency, I think maybe this one could be a skid buffer. Does that sound right? I think that would make sense. So there's actually a no worries, 286 tech. But I'll definitely check that out. I appreciate the tip. One of the things that I've totally glanced over with this is memory mapping, because not only do these need to issue, they also need to specify which of the replicas the data is actually meant for, and then whatever bits are left of the address need to go straight through to the replica. And so what I'm thinking about doing there is actually having the memory mapping outside of here. And then the issue here, part of this port is it's basically going to expect 2 addresses. One of them is going to be an ID for the replica, and then the other address is going to be the address that's actually sent to the replica. And then this unit doesn't really have to worry about that. Although it might be useful, at least in the code that I'm writing, to be able to have this handle some of that. So the RTL itself, I don't know whether or not it makes sense for the memory mapping to live inside or outside of this unit. Probably outside I think it makes it simpler, but the code, the meta programming code that I'm writing for this, I want it to know about the memory mapping. And the reason is I'm thinking I can generate memory map docs from that, to make sure that they're always up to date. Or maybe that's overkill. I'm not entirely sure. But yeah, that's one thing that I'm still ignoring here, that might need to be issued or might need to be dealt with later. I'm going to export this diagram again. Commit it again. All right, so we're an hour in to the stream, and might be time to actually do some real stuff. Although this is real stuff, it is very important that this is documented properly. But I do think I actually want to continue working on a version of this that supports multiple replicas and getting that working before I focus on writes. Because again, I think writes are going to be really easy. The arbitration here is going to basically be the same. Then this unit basically ignores these FIFOs. And then writes again are fire and forget. So I think only this side is affected with writes. And I think that'll be in a really natural way. I think that the bigger unknown is how I'm going to handle multiple replicas. So we can focus on that. Now, again, the buster that I have right now, you don't actually have it add more ports or anything. Although maybe I want to actually start doing that already. Maybe that's what I want to focus on next. Either one of those would be a good thing, because I'm not entirely sure how either of those things will work. But I guess right now, the thing that's closer to the current design would be to be able to specify multiple primaries. I think I actually do want to do that first. Yeah, I'm going to do that. And then this test that I have right now, actually, No, I think I want to put that off, actually, because I want to think a bit more about how I'm going to optionally have these FIFOs or not. Because if you only have a single primary, you don't need or want this FIFO to say which primary the data is going to go back to. I could make it anyway, but I think that's just really wasteful. That also means we need more tests for those cases. But I think, again, like all these tests are very generatable because we pretty much want to just test like the whole matrix. Primary n going to reading and writing from replica n. And then we want to do these kind of weird switching tests as well eventually that are going to like do some of the craziest traffic we can think of that we know how to verify and actually pump that through there. So, but again, I think we can generate all of that. So that should be okay. Yeah. So then let's actually do that. Let's work on multiple replica, but still only writes. Let's focus on that. Let's not get push. I want to do cargo test actually. And again, I only have these 4 tests. They're too basic so far, but we're gonna get there. So I think what I actually want to do is basically comment out these other 3 tests and just focus on extending the first test to be able to basically duplicate this so that we read from the different replicas. So single read primary 0 underscore replica 0. And for these tests, I just want to hard code a unit with 2 primaries, 2 replicas. I think that's what I want to do. So then we're going to have the same test be primary 0 and replica 1, but we'll actually get to that. So we're going to change what we need to change to make this test work sort of as is first. And again, it's going to get more complicated because we need to add all of this other replica stuff. We need this FIFO per replica, so I'm actually going to call this, I think I call this data FIFO right now. But this is going to be called something different. Initially, we'll just call this replica FIFO. And again, we need one of these for, well, first we need the replica FIFO for which replica we issued to. And then we also need these different data FIFOs. And I think actually this needs to be called like replica data FIFO to make sure that those are different. Because again, that models these in the current code, not this. So we can add the replica FIFO as well, which will basically just copy this primary FIFO. Hook it up. Now I think this actually will not generate code now because we have now an instance that where an input isn't driven, so it'll tell us cannot generate code for module Buster because Buster contains an instance of module Buster replica FIFO called replica FIFO whose input read enable is not driven. It's a big long error, but it gives us all the information that we need. So that's kind of funny. But this issue arbiter, I think, doesn't change, but the issue unit will change because now we have this replica bus ready and we also have this primary FIFO ready. And in addition to that, we need the replica FIFO full and ready because we need to write into both of these FIFOs. In all of these cases, we need to do and replica FIFO write ready. And again, this won't fan out more as we add more primary or as we add more replicas. And in fact, this unit won't fan out more as we add more primaries either. However, some of these, like this address, might need to change. I do like that primary and replica have the same number of letters, by the way. I think that's nice. Oh no. How did these get misnamed? No, that is actually correct. Because this is which primary we're writing to. So that is actually correct. But then this one needs to change. Because we need to know which replica that we're addressing. So yeah, so there we need to, again, extend this interface here. So I don't think I've published it anywhere, but I did start working on some kind of spec for the buses. And I think I also talked about this last week. So I'm not going to get too far into this. But I figured out what all the different signals are going to be and how I want them to interact. But I actually need to extend this with some buster specific signals, which again is going to be which replica is being targeted. So I think what I want to do is there's this bus adder, and then there's also going to be some kind of replica ID, and this needs to happen per primary. I thought also about that's funny, Mad Triangle. I thought also about having Buster always pull off the top number of bits from the address, and it would take however many bits it would need to split the address range evenly among the replicas. And maybe that's actually still a good idea. In fact, if I do that, one thing that I kind of like about that is that then it's all automatic, including the memory mapping stuff. Maybe I actually want to do that. Mad Triangle, I really like Rust, and I've been using it for, half a decade now. Crazy. My language of choice before fluctuated a lot. In fact, I think I was doing F# mostly before Rust. Professionally, I had done a lot of C and C++ and C#. But in my personal projects, I experimented with a lot of stuff, and I think F# and Rust have been my favorite. But at work, I do mostly C and C++ in assembler, and then some Rust, actually. But yeah, then this address bit width thing is going to change a bit. I definitely prefer Rust over C and C++, hands down. I prefer it a lot. I mean, definitely it is also dependent on the domain. Like, for example, this project that I'm working on now, this Xenoing project, we're using Rust for all of the hardware prototyping. We're using Rust for, in this case, actually describing the hardware as well. I have my own HDL, which is a Rust API. But the ROM that's going to run on the system is just going to be C. And that's because I can't be bothered to set up all the environment and everything to cross-compile Rust for risc-v. So there's sort of a technical barrier there. But if that weren't there, and I think I also need to get like a C library implementation running. I can't be bothered. So yeah, so if it weren't for that, I would use Rust for the ROM and everything too, I think. I don't think you need to be scared about jumping into Rust, even though you're invested in C and C++. Never hurts to learn more languages anyway, whether it's Rust or not. But personally, I'm happy about Rust. Yeah, I can imagine going back and forth a lot for game dev. I imagine to stick with it, but One of the things I definitely miss with Rust is better performance profiling. I would like a better story there at least. And also, I guess a lot of the things that you know are safe that are common patterns or game dev can be difficult in Rust. Although we do all of our demo scene stuff. I'm in a demo scene group called Logicoma, and we do all of our 64K intro stuff in Rust, which it's pretty good for. Although we get most of the benefits there in the tooling rather than the actual runtime, which could just as well have been C or C++. Yeah, I ended up committing to doing my own HDL. I can post it in the chat if you want to take a quick look. It's not super amazing, but it's similar to Spinal HDL, and it compiles to either Verilog or a Rust simulator, and that latter part's kind of key. It makes it really easy to just hook up simulators into Rust, which I really like. Thanks for the sub, Mad Triangle. Really appreciate it. So yeah, that's kind of what the HDL is about, and it's a bit less verbose in a lot of cases. So all of this code you're looking at on the screen right now is actually using that API. So that's fun. So yeah, I think I want to commit to automatically pulling bits off of the address depending on how many replicas you have. I think I want to commit to that, and again move towards this API where I can create a buster, add a bunch of primaries and replica ports, and then eventually actually generate the RTL. That's great, Mad Triangle. I really appreciate it. Yeah, Spinal HDL seems quite cool. And in fact, it was kind of an accident that Kaze, which is what mine's called, ended up being really similar. Because it was, I think last summer I experimented with some stuff in Python, and then this is basically the same design but implemented in Rust, which is initially what I wanted to do, but I had some trouble coming up with how the API should look and work ergonomically. So then I kind of prototyped it in Python, and then once the pattern was there, then I ported everything to Rust and figured out some more stuff. And actually, the current implementation, even though it's a published library, it actually doesn't generate Verilog yet, but I just don't care because I think it was useful to go through the motions of publishing it. And again, it does the Rust simulator generation, which is, I think, the harder part. So that works, and that's what I focused on. And then at some point, one of these weekends, once this stuff in simulation is mature enough, then I'll just go through and implement the Verilog gen. And I just think that'll be relatively easy. So I can actually just post my demo scene group on Poe. I can post that link for you. So there's our Poet link, and in particular, I would recommend watching this demo, and this one is really popular, and then anything else that's on there. Appreciate the interest. I think it's I like to do streams breaking down like the most recent demo whenever we do one, so if you're interested in that stuff, then you definitely pick the right sub. Yeah. So yeah, so I want to do replica. We can call replica select bits, and in this case we'll do 1, and we'll say to do derive from number of replica ports. Oh, you have? That's cool. Appreciate it, guys. Yeah, I'm really proud of our work in Logicoma, and we're not done. So, although we're probably going to be a bit quiet this Easter, but it won't last for long. And so then we actually want to gonna select bits. Exactly, I'll comment. That's exactly what we're gonna do. Yeah, keep me in line. We'll make sure we kick more ass when we come back. Let's see. So yeah, so then all this stuff will actually just be the same. It'll just have one less address bit there. And then the top bit will be used to select the stuff. I think that'll make a lot of sense. And then in this build directory for the sim test, or this build file, I think I actually will just end up specifying an additional bit here for this initial test. And that way the test itself won't have to change. It's just there's going to be a top bit that's going to select which one of the replicas that we target. And that'll be a good test, actually, because then this code will be exactly the same when we target the other replica, except all the addresses are going to have that that 1-bit set. Although I guess for this test it won't matter, but for some of these other ones, like these read all ones, then it's going to make a difference. Yeah, I should link some of this breakdown. In fact, I think actually on the Poet links, on the individual demo pages, I think we link the breakdowns. Maybe not on all of them. It looks like Trash Panda doesn't have one linked. Dope on Wax does, though. No, it actually doesn't. That's strange. I think I need to fix that. Elysian has a breakdown video linked there. Then I'll actually take a minute and get the YouTube link for that playlist for convenience. I can spam that in the chat. There you go. Whoops. It's so confusing if I accidentally click on one of the videos and I hear myself talk in my own ears. But yeah, thanks for the interest in the sub. I really appreciate it. Yeah. So I think that this issue arbiter, it doesn't actually really need to care about which replicas are ready or anything. I think it just needs to pass on all of the address bits. But I think I'm going to break up the address into the different select and address bits at the arbiter. And then I'm going to treat them as separate signals for the issue module here. I think that's what I want to do. Or actually, I could separate them on the inputs. Maybe that makes sense. Now let's do this. Let's do replica adder bits. I think I use bit width everywhere, so we're gonna call this bit width, and then replica adder bit width. And then these inputs still have these address bit width things here. And then yeah, so we'll do this. We'll do m.output bus adder, m.output issue. Replica select. And so yeah, so this bus adder here, yeah, we can split it off at this level. I think that's nice. So we can do bus adder dot bits, and for this, I'm actually gonna do it this way. So this will be bits something down to 0. I know that for sure. And I think I'll just do Yeah, replica adder bit width, actually. That. And then this one will be bus adder dot bits, and this will be adder bit width down to the replica adder bit width. Is that correct? No, it's totally not. Because I think this is going to end up being 2 bits now, because it's inclusive. So I think we do +1 here. I think that's what we want. Yeah, I think that's it. Or second guessing again. I think actually we want this -1 and this like this, and then this -1. I think that's actually more correct because these are inclusive bounds. Yeah, this feels more correct to me. So in this case, if this is this -1, we're still going to get 1 bit there. Yeah, this is happy with this. Yeah, then this passes back up to the primaries. Good. So again, I'm kind of writing like the unrolled version here, and then hopefully the patterns emerge for making this more configurable. That's kind of my hope. So the issue unit. We could actually also do this split in the issue unit, which maybe is a better idea. I think I'm actually going to do that. Go back to this. And then we just pass on this bus adder. And then when we issue, then we can dump the select in the FIFO, and then the adder is here. Yeah, I think I'm going to do that. And then this again is going to be adder bit width -1 down to the replica adder bit width. No, the other way. It's this -1 down to 0. Yeah, it's addictive, Mad Triangle. Really addictive. But yeah, here in this replica FIFO write data, this is where we do issue r bus adder dot bits, and then we have the adder bit width -1 down to the replica adder bit width. Yep, and then this fans out. In fact, probably what we want to do is do like this. Let replica equals this other thing. I think I want to call this replica select, actually. Yeah. And again, this needs to fan out. Hubertino, thanks for the follow. Yeah, because this needs to do, for example, 0 and 1. And we might need to make this a little more complicated. So I think both of these addresses are the same. So we can do let's replica bus adder is going to be this whole thing here. Then we can dedupe it. Because we'll send the address to both, and then we'll just send enable to whichever one should be enabled. And in this case, since replica select is just this, let's do let replica bus enable is this whole thing here. And then we'll and not replica select. And here's this and replica select. Something like that. Yeah, I think that makes a lot of sense. And then that might be it for this half, except we need to fan out these ready signals and everything. And we also need to hook up this replica FIFO. So we'll do this. Copy this here. And primary here becomes replica, actually for all of this. And this issue here has this replica bus enable and replica bus adder, which we are now going to fan out. It's going to be 0, 0 here, and then 0 down here too, and 1, and 1. If I can type. And then replica bus ready here needs to also fan out 0 and 1. Replica bus ready 0 on instance of Buster issue, but no such input with this name exists. And that was again on Buster issue, so that's this unit, which I guess we haven't done. Right, that's true. That's true actually, because we need these for both of these. Yeah, and this is where this will get more complicated, because which replica is ready depends on the select value. So maybe it's just this actually. Let replica bus ready is, we can do replica select dot mux, and then there's the true case. So this will be replica bus ready 1 or replica bus ready 0. Yeah, I think that is that. I think that's all that takes. So this probably at least generates code and then fails in the build. No, it still doesn't, because Buster issue has an input called replica FIFO full, which is not driven. That's true, because we have this primary full thing here. Yeah, it's here. That we need to drive the same for the replica here. Oh, is the picture-in-picture a Firefox feature? I actually didn't know. I noticed it was on YouTube, and I thought it was a new YouTube feature that I started using and quite liked it. But it's generic to Firefox. Yeah, it is. It is for Firefox too. I can see that I can do that on my stream. Cool. Yeah, that's really nice. Yeah, replica read enable is not driven for this replica FIFO. I'm gonna do this. We'll do m.low. Just because I want this to generate code at least. And it did. It generated code there. Really? Do I have a read? Oh yeah, because there's no address. It's a FIFO. So yeah, read enable would be the only missing one. And then of course, if we look at the test, it has some errors there because now we have replica bus ready. And this actually now is 0 and 1. In this case, we're only going to assert address 0 because we don't care what address 1 is as long as we know that enable 1 is false. So that's what we want. And then I think the test will build and work still, which is actually a good sign because we actually have now tested some logic that I didn't think would be ready yet, which is that this issue only sends ready signals to the correct replica, which is actually quite good. And in fact, it's probably a good idea to update this other test also while we're doing this. I like to try and do this with baby steps. Also, I'm noticing that I do underscore 0 and 1 here when I didn't do that before. Looks like the primaries didn't do this underscore 0 and underscore 1. They just did 0 and 1. So I'm going to update this to reflect that. Just so that we're consistent. So I find that kind of consistency is usually helps pick out a lot of errors. Okay, and then this bus ready here. So now 1 should be true and 0 should be false. And we only care about adder 1 in this case. And again, there's only one return path right now, as you can see from these tests. And that's because I haven't extended any of this stuff on the other side. And in fact, if we tried to make the tests that read all of the data from one of the sides work, it probably wouldn't. Okay, so this is interesting. So this was 67. This is actually cool because what we saw here is that this assertion failed. It wanted to check that primary 0 bus ready was wait. Did I do that right? This is not actually the issue that I expected. 67 is thought this was false. I mean, I'm okay with making this false here. Although I feel like this should be true still. Because this is signaling to the primary which one of these are ready. And in this case, we're saying the primary 0 bus enable is true. Did I change this? Yeah, this actually changes behavior here because now primary 0 bus ready is now false. Now I actually think though that this is actually correctly spotting an error. And I think that's because this now has one more bit. So we need to do this. 1 beef. I call this 0 babe and 1 beef. I feel like that should actually fix that. Yeah, it does. Right. That makes sense. Because we had now this top bit of this address actually selects which replica. And since we had said that replica 0's bus ready is false, and we had addressed replica 0 with this, then primary 0's bus ready signal should have been false. So that actually makes some sense, I think. It's a bit weird that this one was true, but maybe it just didn't even check that because we hadn't gotten there yet. And in fact, we could do this, and I think it should see that this one on line 68 should be wrong. Which it does, which is a good sign. That's great. So that means it's passing along the ready signals correctly. And we're going to want to do some heavier tests on that eventually too, but for now I think this is okay. And again, I think I actually am going to go full on here and get all of the existing tests working with this. Although actually... not yet, because this is read primary 1. This also should be called read primary 1 replica 0, because I also wanted to read from the other replica here, which I think I'm going to do. Replica 1, and this is going to do... yeah, and in fact, actually... before I do that other one, since this is primary 1 replica 0, I actually wanted this to still be 0 beef for this test. Yeah, right, because here I wasn't supposed to swap these because we're going to return with replica 0. And in fact, that's another thing here, is that I've also named this wrong. Hey, Finrock. Yeah, because I have like ready 0, but really this should actually be called replica 0 bus ready. Bus enable 0 should actually be bus replica 0 bus enable. Adder 0 should be the same. These naming conventions are annoying to keep in line, but it's always worth it. Yeah, and that should align more with what we have there. And then, of course, these will all break, but we'll just fix those. Yeah, because we had switched mistakenly in this test. I had switched these replica bus enable things wrongly. This should be replica 1 bus adder. And actually, it shouldn't be. Because this should also be replica 0 bus adder. Because we're saying replica 0 is the one that we're targeting here with this particular thing. So we've got a whole matrix here that we need to test. So now this failed with 69. That's this one. Replica 0 bus enable. That should be true, because we're targeting that one, not targeting the other replica. So that was another place where we made that mistake. And everything else I think still matches because that was its existing test code. So in this case, primary 0, bus enable. Yeah, we're doing primary 1, but we're still targeting replica 0. So that makes sense. And then this is, yeah. So then it's both of these tests that we actually want to fork, which I will do now. And so this is primary 0 replica 1. And in this case, we want to target replica 1 here. And we want to say replica bus ready for both. Do we want to say that the bus is ready for the one we're not targeting? I think we do not. I think we want to say replica 1 ready is false in this case. And then down here, replica 1 ready is also, no, wait. Primary 0 replica 0. Primary 0 replica 0, yeah. Primary 0 replica 1. So we actually do want to say that that's one. We want it to be like this. Yeah, that's what we want. And so then now the replica, we want to say that bus enable for replica 0 is false and for 1 is true. And then we want to ensure that 1 gets the correct address. And then we pass back the data and everything else should be fine. And so now this is going to be primary 1 replica 1. And in this case, we also want to set up the same thing here and make sure this top bit's set for that address. And then we also want to say false and true here. And check address 1. And I think all of these tests should pass, which is good. Yeah, I wish I knew more hardware too, and more Rust. But I get by, I guess. Okay. So yeah, it looks like this side of things is looking good. However, this replica FIFO, we don't have anything reading from this. We don't have any of this return arbiter taking stuff from different replicas, and we don't have any of these FIFOs modeled yet. This is a bit of a slow process, but again, makes a lot of sense to test all this stuff up front. I'm gonna wait for these read all things because we need to do the same kind of matrix there, and I might actually want to refactor this test code, and even for this one too. We'll see though. I don't usually mind having a lot of duplicated code in the tests because you have each test being very standalone, which is kind of nice. But yeah. So next, what do I want to do? I guess we could work on this replica buffer. Which is going to be important. Its job is basically to always try to read from this FIFO. Like always fill itself with data here. But it's going to have some state too. So let's see. Maybe I should make a new drawing for this. So it's going to have essentially like a read, or there's a FIFO that's going to read from. And so it's going to have some input from that FIFO. And yeah, I actually don't want to bother drawing this. I'm just going to be lazy here. But yeah, we need this replica buffer, I'm going to call it. And I'm going to put it here in the code. Okay, and here we're going to have, let's see, replica FIFO, This is not data FIFO, this is a replica FIFO. And so replica FIFO empty is the one we care about. And we're going to have some internal state here. So let's, I guess, we can say data is m.reg. And it's going to be called data, and it's going to be data bit width. Actually, it's not. It's going to be, because this is the replica, so this is actually going to be replica select bit width. And then there's going to be a data valid is m.reg. Data valid, and that's going to have 1 bit. So we can do data dot default value, and that's going to be 0. I think we need to do U32 for that. And then data valid. Oh yeah, the input here needs to be 1 bit there. Data valid default value is also going to be false, because we know that's a 1-bit signal, so we'll do that. And then we need to come up with the logic for when we should do that. So let's do it like this. Let's next data and next data valid is going to be some stuff. And then we're going to say data dot drive next with next data, and data valid dot drive next with next data valid. And here we're going to have a conditional, and the condition is going to be a couple things actually, because we need a bunch of stuff. So we need, if that FIFO is empty, we need, actually I put this here. We need I guess it's going to be this return arbiter. Is that what I called it? Return arbiter? Yeah, I did call it that. So return arbiter replica buffer read enable. That's a stupid long name that we're probably going to want to shorten, but we'll stick with that for now. And we're also going to want to output these. Yeah, we need the next data, and then if the next data is valid, to be dependent on if the read is enabled. Yeah, so if the read is enabled and data valid is true, then next data is going to be, well, it actually depends. Probably going to end up writing this conditional a few different times. Didn't I have something similar for this? Or maybe I threw that out in the last stream, actually. Anyway. So essentially what we want to do is if it's reading and the data is valid, then this actually depends on whether or not we can read more data. So this is going to then depend on if the replica FIFO is empty. If it's not empty, actually, then we'll do that as the first case. And if it is empty, so if this is going to be read and we don't have more data coming in, then next data is going to be, doesn't actually matter what next data is. We could have it be the current data. So let's do data.value. And then next data valid is going to be false. If we have read data and if data is being read out of us and we can read from this next FIFO, this is actually kind of confusing because we need to issue the read to the FIFO and then have data come back on the following cycle. Yeah, this gets messy. And I also just saw that's 9. So I'm actually going to go, and then I'll work on this later. Probably going to stop here today anyway. Yeah, we'll do that. All right. We'll break here. Anyway, thanks guys for hanging out, and I'll see you next time, where I hope to have this solved. But yeah, see you guys.